It feels like we should just point a rocket at 3I Atlas and go, but the physics is brutal. When it was discovered on July 1, 2025, the comet was already inside Jupiter's orbit and barreling in at about 137,000 miles per hour, later peaking around 153,000 miles per hour near the Sun. Because its path is steeply hyperbolic, a probe from Earth would need an enormous change in velocity, way beyond what chemical rockets and even most advanced concepts can deliver. A July 2025 study concluded that any post-discovery Earth launch isn't feasible. The change in velocity required is outside today's propulsion capabilities. ESA has explicitly ruled out a dedicated probe for the same reason, calling the comet's speed and short window technically impossible for a new mission. Future standby interceptors might one day be waiting in space for such visitors, but for 3I Atlas, that train has already left. On paper, 3I ATLS sounds like a once-ever miracle. It's only the third confirmed interstellar object after 1I Oumuamua 2017 and 2I Borisov 2019. But the small number we found is mostly about our eyes, not the universe. Until recently, our sky surveys were simply not sensitive enough or fast enough to catch these tiny, faint, fast-moving objects. Models of interstellar debris suggest that several interstellar objects, roughly the size of Oumuamua, probably pass inside Earth's orbit every year, at around 10,000 may be inside Neptune's orbit at any given moment. NASA's Hubble team even calls 3I ATLS one of a previously undetected population that will gradually emerge now that surveys like ATLAS, Pan-STARRS, and soon the Vera C. Rubin Observatory are online. So 3I ATLS is rare in the sense of hard to see and scientifically precious, but objects like it are almost certainly all around us all the time. This is the most dramatic idea and the least supported by evidence. A small research group has publicly speculated that 3I/Atlas might be some kind of engineered craft, partly because of its non-gravitational acceleration and odd features like an anti-tail. But every new measurement pushes the story in the opposite direction. NASA, ESA, and independent teams see classic comet behavior: an icy nucleus, a bright coma, dust and gas tails, and outgassing that naturally explains the small trajectory tweaks. Most strikingly, radio observations with the Meerkat array detected emissions linked to hydroxyl, OH, radicals, produced when sunlight breaks apart water molecules, exactly what you expect from a normal water-rich comet, not a transmitter. The scientific consensus is overwhelming. 3I/Atlas is weird, yes, but weird in a natural comet-ish way, not an alien starship way. The key evidence is not a guess, it's written into the orbit. 3I IATL Atlas follows a strongly hyperbolic trajectory with an eccentricity of about 6.1. Far beyond any normal comet, and far too high to be bound to the Sun. Inbound and outbound, its interstellar speed, the velocity it has far from the Sun, is around 58 kilometers per second, much larger than typical solar system comets. Careful reconstructions show it didn't pass close enough to any planet to gain that energy from a gravitational slingshot inside our system. So it can't be something we kicked out ourselves. Its high velocity and one-way, non-closed orbit prove it is simply passing through and will never return. In other words, the math leaves almost no wiggle room. 3I IATL Atlas must have been born around another star. If you trace 3I/Atlas backwards, it seems to arrive from the direction of the constellation Sagittarius, roughly toward the Milky Way's central regions. Its speed and motion suggest it belongs to the galaxy's thick disk population, an older, more slowly rotating component of the Milky Way. That implies an age of roughly 7 to 14 billion years, potentially older than our 4.6 billion-year-old solar system. Over such a huge timescale, the object has orbited the galaxy many times, passing near stars and gas clouds that nudged its path with tiny gravitational kicks. A recent study found it likely came within about 1 parsec of at least 25 known stars in the last 10 million years alone. Those countless perturbations smear out its trajectory, so when astronomers try to rewind the tape, the path fans out into a vast uncertainty cone. We can say what kind of region it came from, but not which specific star was its original sun. Early on, some images made 3I ATL look oddly tailless, feeding the idea that it didn't behave like a normal comet. As it approached the sun, that changed. Hubble and ground-based telescopes now clearly show a coma of dust and gas and a developing tail, just as expected for an icy body heating up. Later, there was a brief period when it seemed to lose its tail after perihelion, but careful follow-up showed this was an illusion created by viewing geometry and sensitivity limits. The tail was still there. On top of that, astronomers have reported a puzzling anti-tail, where dust appears to point roughly sunward. This can happen when the dust sheet is seen edge-on, making the tail look like it's pointing the wrong way, even though gravity and radiation pressure are behaving normally. So, 3I ATL does have tails, and they're giving us a masterclass in how perspective can trick the eye. We couldn't send a dedicated spacecraft, but we did throw almost the entire modern observatory zoo at 3I.Atlas. NASA has lined up a multi-mission campaign. Hubble for sharp visible light imaging and size estimates, James Webb Space Telescope, JWST, for infrared spectra revealing ices and gases like CO2, Spherix, TESS, SWIFT, and large ground-based telescopes, Gemini, Keck, to track brightness changes, color, and composition over time. Meanwhile, Mars orbiters, ESA's Trace Gas Orbiter and Mars Express, plus Tianwen-1 and NASA's Mars Reconnaissance Orbiter, took advantage of the comet's October 2025 Mars flyby to grab bonus images and spectra. There's even hope that Juno and JUICE can observe it during its passage through the outer solar system, though they can't be redirected to fly past it. So, while no single probe is chasing 3I.Atlas, a virtual fleet of telescopes across the solar system is dissecting this visitor in exquisite detail. ATLAS might be one of the oldest solid objects humanity has ever studied. Its motion hints that it belongs to the Milky Way's thick disk, whose stars are typically 7 to 14 billion years old. Two independent studies in mid-2025 used this dynamical membership and galactic models to estimate the comet's age. One found 7.6 to 14 billion years, another 3 to 11 billion years, both comfortably older than our solar system. That doesn't mean the comet itself formed before its parent star, but it suggests it condensed out of a very ancient protoplanetary disk in the galaxy's early days. Since then, it's likely completed multiple orbits around the Milky Way, slowly darkening and reddening as cosmic rays baked its surface, a process that could explain its unusual color and heavily processed outer layers. In a sense, 3I Atlas is a frozen fossil, carrying chemical memories from the deep past of another solar system. This is backwards. Astronomers didn't predict 3I ATLS and then wait for it to arrive. They noticed it first, then ran simulations. The comet was discovered as a moving point of light by ATLAS on July 1st, 2025, at about 410 million miles from the Sun, and only afterwards did teams dig up pre-discovery images from May 2025. Before it was bright enough to show up in survey images, it was effectively invisible to us. Long-term orbital integrators can predict the motion of known objects, but not of an unknown, tiny comet that reflects almost no light. Once 3I ATLS was identified, astronomers used its observed positions to compute a precise hyperbolic orbit and then project its future path, perihelion in late October 2025, closest approach to Earth in December, and eventual exit from the solar system. So simulations are crucial, but they start after discovery, not years before. If there's one result that made scientists say, "Wait, what?" It's the chemistry. JWST observations showed that 3I/ATLS has an extreme CO2 to water ratio of about 8:1, far higher than typical comets. Only one known comet, C/2016 R2, comes close to this level of CO2 richness. This CO2-dominated coma likely means the comet formed far from its parent star, beyond the CO2 ice line, where carbon dioxide can freeze into solid grains, or in an environment with intense radiation that altered its ices. Another possibility is an insulating crust that traps water ice while letting more volatile CO2 escape first, making the coma appear CO2 heavy until later. Rather than pointing to alien tech, the chemistry tells us 3I/ATLS comes from a very different kind of planetary nursery than our own. Each spectrum is basically a postcard from that distant, long-gone disk, hinting at how diverse other solar systems really are.